I apologize already. I think my voice is not doing so well, as you can hear, but let's try to make most of it. And I'll start by summarizing the main thing that we have done so far in the last 2 lectures or so. So what we found is we put in a quantum number p, just ad hoc, just by hand. And what that gave us is that the unperturbed energies over to 1. One way you can make sense of this equation is to say, oh, this p was really irrelevant. Drop it. Everything is fine. But otherwise, we know left-hand side does not have q, right-hand side does not have p. There is a more general solution that still obeys this equation, which is to choose the wave functions in momentum space, the unperturbed wave functions, as delta pq. We made that choice. We showed that this is a perfectly valid choice. And using that choice, we plotted the band structure and we saw many branches. And we saw degeneracies at the zone corners, at the corners of the first Brillouin zone, and at the center of the first Brillouin zone. Then, when we add the periodic potential, there is a gap that opens up at this degeneracies. So, if I want to plot the lowest block band now, the picture with the periodic potential looks like this. And then there will be higher bands and so on. But this is the lowest block band, and a gap opens up at the zone corner. This already includes the effect of periodic potential. So next, what I'm going to show is an important theorem in condensed matter physics. It's called Peierl's theorem. And it is very easy to understand using simply this band structure. So there will be higher bands also. What this theorem says, it only deals with the lowest block band. The statement is one-dimensional, equally spaced chain is unstable at half filling of the lowest block band. So if you have a system where the lowest block band, if you have a one-dimensional chain, equally spaced chain, and the system is such that the lowest block band is half filled, this system is unstable. It cannot exist in nature. So this is the theorem, and we can understand it quite easily from this band structure. So the first Brillouin zone is K belonging to minus pi by A and pi by A. So when I write this, this also implies, now we have imposed periodic boundary conditions. So what that means is K, it can only be a multiple of 2 pi over NA, where NA is the total length. So N is the total number of sites, A is the lattice constant, and this small n is some integer number. These are the only values that K can take because we have imposed periodic boundary conditions. So if not periodic boundary conditions, there could be some other boundary conditions. As a result of that, K will get quantized. But you want to restrict K to the first Brillouin zone. And in this case, this implies that this integer n is restricted to minus n by 2 to n by 2. So how many values of K are allowed in the first Brillouin zone? So in the first Brillouin zone, so there are total n states. That means n allowed values of K. Now in this problem, let's for the moment forget spin-off electrons. If you consider the spin-off electrons, then all these states will be doubly degenerate, and we can account for it later. So in first Brillouin zone, there are total capital N states. Now, if the system is half filled, that means half of these states are occupied. That means the total number of electrons that the system has is n by 2. What that really means is you have a one-dimensional equally spaced chains, and you get this band structure, and then you have n by 2 electrons, and you start filling them up at T equal to 0, at 0 temperature, and you want to calculate the ground state of the system. So the first electron you put at the lowest energy and then keep adding. Keep in mind that there is Pauli exclusion principle, so each state can only be occupied by at most one electron. And when you fill up n by 2 electrons, you will be somewhere here. And because of this quantization, you can check that the value of K will be half of this. So will be pi over 2a and minus pi over 2a. So all these K states, so I'm drawing like a continuum, but imagine that capital N is very large. These are essentially discrete points in momentum space. And all of these K values are, the states corresponding to these K values are occupied. So the theorem says that this system is simply unstable. Let's consider now an example where, so this is the chain we started with. Let's assume that every other site moves either to the left or to the right spontaneously. What that means is this side does not move at all. This side moves to the left. This side does not move at all. This side moves to the left. This side does not move at all. That moves to the left, and so on. And it can also move to the right. So the first side does not move at all. The second side moves to the right. Third side does not move. Fourth moves to the right, does not move, and so on. Now, if this happens, you can see that the periodicity of the system is now doubled. So this distance is now 2 times A. Any questions? So if you want to describe this by a lattice, the periodicity is going to be 2A, and at each lattice site, now you will have 2 atoms or 2 states. So this is similar to the example that you did yesterday in 2 dimensions. But this can happen, and we are assuming right now that this happens spontaneously. If this were to happen, let's see what will be the implications. So if I want to now calculate the first Brillouin zone, so this doubling of the lattice constant is also called dimerization. There will be a tutorial or a homework problem on this, so you will learn more details how to do this. Our goal now is to calculate the first Brillouin zone for this dimerized lattice now. So the first Brillouin zone, the new first Brillouin zone, now will have block vectors between minus pi over 2a and pi over 2a. So what that means is if I were to calculate band structure of this system, what I will find is, I'm drawing it here. I hope it's visible. Should have left more space. So this is energy as a function of K and K. And now I want to plot it only in the first Brillouin zone, which is pi over 2a minus pi over 2a. So what I've done here is I assume that dimerization happens, either left or right. I calculate the band structure, and I'll see as a result of periodic potential now. So the unperturbed, if there is no lattice at all, then it will be like this actually. Well, there will be degeneracies at pi plus minus pi over 2a, but the periodic potential will open up gap. So this will be the spectrum of the dimerized lattice. Now you can see that electrons, compare this case with this case. You can see that electrons have now lowered their energy.
Or if you were to draw that plot on top of the other one, how would it look? Because I'm kind of like having trouble in.
So I'm doing qualitative. So essentially, how it will look is really start from here. Band structure will be different. For example, what I mean by that is the derivatives of this and second derivative, so on. There will be some differences, but the number of states or this energy value will be higher than this energy value. And that's the only thing we care about. So this, let's say E naught is here. Now another thing is, we said that this one-dimensional chain is half filled. That means there are n by 2 electrons. If you calculate, so total there should be n by 2 states. Here we know that these total are n states, so these are n by 2 states. If you do the same thing here, you will get now the half-fill lattice corresponds to this filling, and you can check this because now each lattice side has 2 ions and it can take 2 electrons. So the half-filled or n by 2 electrons in this lattice corresponds to this situation. You can convince yourself of this. So by dimerization, the total energy of the system has reduced. Well, not so fast, because you have to pay some energy cost for this to happen also, right? To move ions, it costs energy. So what really we are saying is, for a given strength of periodic potential, this gaps, or by how much we have lowered the energy, really depends on the strength of the periodic potential, given a certain strength of the periodic potential, you can find a small displacement such that the energy cost is more than compensated by lowering of electronic energy. So the energy it costs to move ions by a very small amount will be small, by large amount will be large. And for a given strength of periodic potential, you can always find some small displacement such that this happens. So essentially, this effect could be very small, but in some cases, it is quite large. There is one case which applies to polyacetylene, and there are very interesting topological properties of this material. It's a one-dimensional chain, and we'll do a problem on this in the tutorial or in the homework. And you'll learn more about this. Yes?
Is this only in one dimension or?
Yes. So this chain polyacetylene, for example, it's carbon-hydrogen, alternating double and single bonds. It's a one-dimensional system. So this model applies here. Any other questions? Yes.
I'm not really sure what you mean by sites moving to the left or the right. What's left, what's right? How?
So this is, you remember this Hamiltonian, the big Hamiltonian that we wrote down? There was a term there, ionic kinetic energy. That we will show. So after this, we'll deal with electron-electron interactions. But after that, next week, we'll talk about phonons. And they really correspond to kinetic energy of electrons. So these ions are not necessarily stationary. So here I just assume that this happens, but later on you will see that you can imagine these ions as being connected by springs. So they can move, and essentially it's a new kind of lattice that is emerging because so you can think of it as a spontaneous change in the system because the new system is the lower, free energy is lowered. So you can think of it in terms of a topological phase transition, and the problem also will discuss this a bit. But I see your point. At the moment, we have not talked about mobility of ions, but in principle, ions can move and get frozen if the system can actually lower its energy by choosing the new location as the equilibrium.
So basically it's saying that kinetic energy of ions is sometimes less than the Coulomb push from the electrons, which then is more efficient for the system to push them to the other side.
Yep.
Okay, thanks.
I mean, this also ignores a lot of effects like ion-ion interactions and all this. But the point is you can always find some small displacement such that it happens. So it's a matter of saying that this is a theorem and this will always happen. But what will be the implications of this in experiments? Can you measure it? And you can if this effect is large. By that I mean that this displacement is really large. So that really depends on the structure of phonons and so on, which depends on what kind of ions are involved and properties of those ions. And we'll discuss phonons in detail, and then we'll also discuss electron-phonon interactions in detail. So we'll get to all of this. It will be clear later on. Any other questions? So next, our goal is to understand when electron-electron interactions are relevant. So our goal is to calculate average kinetic energy per particle and average potential energy per particle. Now, let's speculate, and somewhere after 15 minutes or 10 minutes, we'll prove that this is wrong. So let's speculate. When do you expect the potential energy to be large? When electrons are very close to each other. That means that the density of electrons is very high. Does everybody agree? If you don't agree, it's okay, because I've already told you it's a wrong answer. But intuitively, you will guess that when the electronic density is large, electrons are close to each other, and Coulomb interaction should be very relevant, right? This turns out to be not the case, and that's one of the reasons why we spend so much time in understanding non-interacting properties. It depends a lot on the dispersion relation of the electrons, and it depends on what kinds of bands. So it really depends on average kinetic energy per particle. Pauli exclusion principle plays a very important role, and it turns out that in many cases, or most cases, depending on the band structure and everything, for free electron gas, for example, this is simply incorrect. Actually, at lower densities, potential energy is relevant. So, well, thankfully, lower densities are easier to realize in experiments. So the novel effects associated with interactions are actually quite easy to see in the experiment. So we are going to spend next few lectures discussing this. So let me show this quickly. So we can write this kinetic energy of electrons. So in the course of doing this, I will also introduce some terms that are used in condensed matter, like Fermi energy, Fermi wave vector, density of states. And the idea is just to learn these definitions, and then you will also have problems. In the tutorial, you will do some problems where you'll learn more about these quantities. So the kinetic energy of electrons is sum over spin sigma d cube r So this is a single particle operator. This can simply be written as, this can also be written as the dispersion K, Ck sigma dagger, Ck sigma. So we can define these, let me just write down once in this lecture. So these Ck sigma are defined by 1 over square root of volume integral d cube r e to the power I k dot r psi sigma r. So in general, we now know that this dispersion in a solid can be very different. If you have tight binding model, for example, a 1D tight binding model gives minus 2t cosine Ka. But in general, in 1D, you have many bands. Now, in the 2D, you will have two-dimensional bands. In 3D, it's three-dimensional, so energy depends on Kx, Ky, Kz. You can have very complicated band structure. And you will have many bands. So you will have another index n, and you will sum over all band indices n, small n. And these operators will also have the index n. So this is basically the kinetic energy. So you can generalize this to bands also. What I'm going to do next is I will do for free particles where the dispersion is simply parabolic, but you can extend it to bands by just putting that dispersion and assuming that there is sum over n. So there is a straightforward extension to the case where you have a complicated band structure. So omega is the total volume. Let's write this as Lx, Ly, Lz. Lx is the length in x, Ly length in y, Lz length in z. And we know that the wave functions, we have chosen here momentum eigenstates for our second quantization. And momentum eigenstates, so the wave functions are kxx So next, I'm going to impose periodic boundary conditions. That I'm simply saying that the system is such that the wave function, if you add Lx in x hat, is same as phi kr. So it's like in x direction, if you add the total length, you get back to where you were. Similarly in y and z. What this means is that imposing this periodic boundary conditions, this will again give us that kx must be, so just use this plane wave form, you can show that this is an LZ these are some integer numbers. Now, let's try to see what all this really means. So what I'm plotting is this energy as a function of k. And I'm plotting it as a function of, say, kx. So I'm assuming let me just do it over there. Actually, we have another board. So let's write it bigger. Epsilon k is h bar square kx square plus ky square plus kz square over 2m. Okay, so we'll just draw here. So let's move a bit further. So our goal is to draw energy as a function of k. And I'm plotting this as a function of kx. We've seen that imposing periodic boundary conditions quantizes the values of k. So I'm going to plot this parabola. And these values of, if the integer is 0, get a value here, 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 here. So this distance is 2 pi over Lx. This is the distance between two neighboring k values, kx values. Next, I'm going to denote all of the k values, so k values, they are labels for the eigenstates. So we've chosen momentum eigenstates for second quantizations. They are the quantum numbers. So all the states that are occupied, so states are labeled with kx, ky, and kz. All the states that are occupied, I'm going to fill these circles. So depending on how many electrons you have, some of at t equal to 0, some of these states will be occupied. And this energy, the states, so the definition here is that the states are occupied till the Fermi energy. So n electron, the number of electrons, depending on what this number is, result in states being occupied till Fermi energy EF. So this is the definition. All this state, you start filling up states, and the last state that you put in, the energy of that state is the Fermi energy. That's just the definition. Corresponding to this Fermi energy, you can find a Fermi momentum. Yep, just definitions. Next, we can also look at, now we had epsilon k as a function of kx. What I'm showing in this plot is kx, ky, and again, there will be many states. And the states that are occupied are denoted by So in general, you will plot all of these states that are there and then start filling them up. You will see imagine a similar, the axis kz coming out of the board, and there will be some dots in kz that will also be filled. So you can define all these filled dots, you can enclose in a surface, and everything inside this surface is occupied, everything outside the surface is unoccupied. If Lx is equal to Ly equal to Lz, then this will be a sphere. You can call it a Fermi sphere, and this sphere will have the radius of the Fermi wave vector. So this is a sphere in momentum space, and the radius is kf, everything inside is filled, everything outside is empty. If Lx is not equal to Ly and Lz, in general you will have some ellipsoidal shape. For bands, this can be very complicated because they can, in three-dimensional bands, you can have band gaps and variety of things. And in general, this Fermi surface can be very complicated. It can have pockets, it can be you can have nested Fermi. So there are a variety of phenomena that are associated or can be explained because of the fact that the Fermi surface has a particular structure. In our case, it's free electrons, parabolic dispersion. If we assume Lx equal to Ly equal to Lz, we have a Fermi sphere. So now comes a crucial thing. All of these states are occupied. Let's write this as the ground state. So I'm using this symbol ground state. And in condensed matter systems, most of the time when we calculate expectation values of some operators, we'll always do it in this ground state. In the field theory course that you're doing right now, you're also calculating expectation values, but typically you are doing them in vacuum. So one of the things you may have noticed is that all the annihilation operators acting on these expectation values vanish because you're calculating them in vacuum in field theory. In condensed matter systems, we'll calculate them in ground state. That has a lot of particles. So annihilation operator acting on ground state is not zero. So sometimes the reason I'm mentioning this is in some books or many people use a notation where the ground state is denoted by 0, which is typically reserved for vacuum. So please don't get confused. This is the most common confusion. We are not in vacuum. We are calculating expectation values in ground state, which has a lot of particles. So this ground state ket can be written as for all momentum less than the Fermi momentum, the state with upspin is occupied and the state with downspin is occupied. Now, this is the true vacuum. Oh, dagger, yeah, sorry. We'll also see that this will have some implication when we want to use Wick's theorem here, either today or on Monday, that because now there is a special thing. So if the operator, annihilation operator, acting on ground state has momentum below kf, you can actually destroy something. While in field theory, when you prove the Wick's theorem, annihilation operator acting on vacuum gives 0. Here we have to be slightly more careful, but we'll see that identical results can be derived here also. So annihilation operator acting on ground state is not 0 as long as the momentum k of this annihilation operator is less than kf, because we have electrons for that state. But if you act with an annihilation operator such that the k is greater than kf, it vanishes. Yes?
So if you have, let me think now. So if you have some number of electrons that don't totally fill up the sphere, but fill up most of it, like some with degenerate energy.
Yep.
Like this will still create all those electrons and won't account for the ones that are missing.
So I'm assuming very simple. In that case, the definition of kf will be different. The Fermi wave, the definition is still that of the Fermi surface is a still, and inside this surface all states are occupied. In that case, I will write the ground state as product with k such that k is inside this Fermi surface. So we can just, that's basically I've just written it for the simple case of 3D, but you're right. In general, the ground state is creating all electrons with up and down spin for all k states that are occupied. And it can have very complicated structure. It need not be described by one simple Fermi vector in three-dimensional space. So corresponding to this wave vector kf, you can define some other quantities which is called Fermi wavelength. So Fermi wavelength is defined as 2 pi over kf. You can also define Fermi velocity, Vf. This is simply defined as 1 over h bar. The derivative of the dispersion relation with momentum. So if you are calculating velocity so I'm just writing down this definition and I'll just tell you what it means. You evaluate this at kf. For our case, you can quickly see this means. So in 3D in general, if you're calculating velocity in x, you'll do it with x, y, you'll do it with y, z, so on. So these are just some definitions. Next, we want to calculate this Fermi energy as a function of electronic density. Now, what is electronic density? Electronic density is basically total number of electrons divided by volume. how can we calculate the total number of electrons? We can calculate this quantity, sum over k sigma, and in ground state, so we want to calculate number of electrons in the ground state, is basically expectation value of the occupation operator. There is also an easier way in our case to calculate this, which is to look at this picture here. So we really have a sphere, all lengths are equal, and inside this sphere, all states are occupied. So if I want to calculate number of electrons, I will have a factor of 2 for spin. And what I will have is an integral, or let's say sum over k, over this sum is over all occupied states. Now this sum over k can be converted into a momentum, into an integral. And what we are integrating is essentially 1. So essentially, we are calculating volume in momentum space. The reason I went to all these methods is all these steps is just to get these factors right. So you have 2 omega divided by 2 pi cube, and then the volume of the sphere. So you basically have omega kf cube So you can write the number of electrons in terms of Fermi wave vector. So the electron density, which I'm denoting by rho electron, is simply this number of electrons over omega, the total volume of the system. So this can be written in terms of the Fermi wave vector. This implies that the Fermi energy can also be written in terms of electron density. H bar square, kf square over 2m. This, I will get h bar square over 2m, 3 pi square to the power 2 by 3. So now let's calculate we will calculate total kinetic energy. Now the total kinetic energy, let's use the symbol E naught. Total kinetic energy is given by adding kinetic energy of all particles. So it's simply h bar square, k square over 2m, and then ck sigma dagger, ck sigma. So what this expectation value, it gives 1 if it's occupied, and then it contributes to the kinetic energy. If not, it will be 0. So you can go through the calculation. It's very similar to this. And now you have k square in front. So you will have k to the power 4 integrated over. So you'll get k, you can integrate, you will get k to the power 5. I'm not going to do this trivial calculation. You can do the integral. What you will find is that this can be written as 3 over 5 the Fermi energy times the number of electrons. So this means that average kinetic energy per particle this is this total kinetic energy E naught divided by number of electrons. This is simply 3 over 5 epsilon F, which is proportional to electronic density to the power 2 by 3. Now imagine you have large number of electrons, and assume that the average distance between them electrons is, say, d bar. That means total electrons can also be written as total volume divided by this average distance cube. This means that rho electron goes as 1 over this average distance cube. That implies this average distance, this is proportional to density of electrons to the power minus 1 by 3. Now, average potential energy can be calculated as E square 4 pi epsilon naught average distance. This goes as rho electron to the power 1 by 3. So now we have it, the ratio of average potential energy by average kinetic energy this goes as so now what have we learned? We have seen that if the electronic density is very high, you can ignore the potential energy. Right? So it's seemingly counterintuitive result is another consequence of Pauli's exclusion principle and the fact that we have large number of electrons. So if you have large number of electrons due to Pauli exclusion principle, the states given by the one single particle Hamiltonian can be occupied till very high value of energy. So when you calculate average kinetic energy, it can be very large, and it can have, if you do the experiments, that will have the most dominating effect. However, for when the electronic density is low, then the potential energy, the interactions will have the dominating effect. So next our goal is to deal with these interactions. Before we do that, I will take 1 minute to define a quantity which is used a lot in condensed matter discussions called density of states. And now, be careful with the notations. There are way too many definitions. Now I'm going to write this as rho as a function of E. Yes.
For this average ratio of average potential to kinetic energy, that's only true for the electrons that are that have fairly high energies, right? Like the electrons towards the center won't have that average kinetic energy.
So yes, I mean yes, we have calculated this on average. Yeah. So in a real system, the reason why we have calculated this on average, this is pictured at T equal to 0, at 0 temperature. Essentially, when you are at finite temperature or there are other sources of excitations, there will be many of these electrons will be outside, and there will be holes inside. So we just want to do this calculation with averages just to get an idea of when to expect these quantities to be relevant. And another thing is this. So what I'm going to do next is another crucial piece in this to answer your question. The state at k equals 0 or the low energy, the k values that give you low energy, the number of them is very small. But the k values that give you large energy, the number is really large. So actually they tend to have dominating effect. Does that address? So in short, the density of states which I'm about to define will be higher at higher energies typically. Yes.
So would there be a correction to this calculation? Because when you do this calculation, you calculate the number of electrons in the free case. So would there be a correction when you introduce the potential? Because
you mean if the dispersion is very weird or yeah. So and also if you have bands, for example, say you have, take an extreme case, you have a flat band, you have no dispersion at all, and there's a lot of states, and you can set it to 0 or everything goes there. So all these things would have an effect of whether this average is small or big. And this is a case of 3D, and they do have an effect. So in general, I would say the goal is calculate it carefully and see. So it's not a very general thing that there are exceptions. So if you have some exotic band structure, you could get interactions to have very dominating role even for high, even when you have large electron density. So density of states is defined as the total number of states that are available for occupation at a given energy. So one way to calculate this is density of state as a function of energy. So I will write a factor of 2 for a spin. So it's defined as the total number of states that are available for occupation at energy E per unit volume, because we are calling it a density. So we have 2 for spin, the volume omega, sum over k, delta function E minus Ek. So we can write this formula just from definition. This is the definition. You add all values of k, and this delta function contributes only when the energy corresponding to that value of k is E. So this is really giving you number of states available for occupation at a given energy E per unit volume. So this is the definition of density of states. You can write this as an integral over momentum. Then you will have 2 for spin. You can integrate over the whole Brillouin zone or the first Brillouin zone, and you'll have an integral in momentum to pi cube. And now you have delta function Now keep in mind that you have delta function of a function. So in the tutorial, you will have to derive tensive states for various cases. This is delta function of a function when you want to do it. So be careful. You can use identities to write it as in terms of delta functions in case space and derive density of states for a variety of cases. You'll also see a case where you will have a somewhat messy band structure, and you'll see how this tensive state depends, and that will alter a lot of the discussion that we just had. And there is another formula for this. Let's just write down the formula. It's an integral over a constant energy surface in K space. So this is a surface integral. All these formulas can also be derived starting from the first formula. 1 over gradient in momentum space of the dispersion relation. So now we know when potential energy is relevant. Any questions so far? So now let's change the focus of our discussion, and let's talk about interactions. So we are now assuming that the electron density is such that the Coulomb interaction between electrons plays a dominating role. So our goal is to include the two particle terms in the Hamiltonian that we had. And for the moment, we are just going to look at electron-electron interactions. So in the full Hamiltonian for a crystal, there are also ion-ion interactions and so on. And for the moment, let's just consider electron-electron interactions. What you can already guess is that this is not an easy problem. You have operators, you have 4 operators, and typically it's very hard to calculate any correlation function for if you include this term in the Hamiltonian. So naturally, you would like to develop tools, formalisms to address this in a simple way. There is one important, let's say, so there's something called mean field theory. It's an important tool in the sense that if it works, it simplifies the problem drastically. And also, it's not very easy to figure out the mean field that this theory you need to calculate. So there are many ways to do this mean field theory. I'm going to present this formally. You should keep in mind that this is just an idea. You can have many variations of this idea. And I would say that from experience in condensed matter systems, materials, this has been a very successful way of approaching the problems. And later on, we'll discuss Hartree-Fock theory, which is also applying this to a bunch of electrons. For the moment, let me just present the idea. Any questions so far? So now we want to deal with interactions. We know they are complicated. So we are looking for something tractable, something that we can gain some insight into what interaction does, to understand what will be the effect of interactions. If we start with these single particle dispersions that we have, what will interactions do to these particles? So have you discussed self-energy in the field theory course? So there will be some things that you would also see in field theory corresponding to what we will do, and we can make a connection between both of the courses. So let's talk about the idea. So in general, you have So I'm closely following the textbook also, and we'll just have a bit more discussion than the textbook has. So if you have any questions, just stop me, and you can read this also in the textbook. So I'm just showing a box with some particles, bunch of particles. And this is the real system. The idea is to replace this system by a new system which has one particle. This one particle can be very different. Can be very different, one single particle from what we started with. And all other particles where they were, they're now empty. They're not there. And we replace all other particles by some average density. So essentially, this is mean field theory. Now, this seems like a very crude approximation. In general, motion of one particle, say this particle at this coordinate r, depends on coordinates of all other particles. Moreover, if these are electrons, if you have an electron here, in general, you don't expect other electron to be very close to it. In fact, you would expect it to be further away. So you don't expect electronic density will actually be suppressed around this electron. So what I mean is, imagine there is an electron here, then there will be an electron here. So if you think about electronic density, it is finite here, it is finite here, but close to where it is finite, you'd expect some suppression in electronic density because of Coulomb interactions. So to replace the density by some average seems like a very harsh approximation. So I'm just trying to, some words of caution that this approximation is really, we are assuming a huge, it's just, let's assume that this can be done. It's just an assumption, but it does not seem like a very good idea to start with. So what we are really doing in this approximation is we are taking into account the interactions, all the interactions between all of the electrons, all of the correlations, but on average. It turns out that this theory indeed works and can be verified in experiments, and actually it works very well. The reason it does work very well is we choose this average field in a way that is motivated by physical symmetry, some symmetry arguments, some conservation laws, and so on. So if we choose this average density of particles that this one single particle sees in a clever way, we could get a good description of the real system. And now you just have one single particle that sees some average density, and the Hamiltonian will now only have single particle terms, and you know what to do with that. However, this will not be the single particle term that you had in the original system. In fact, there is something called self-energy, which is a correction to the single particle terms in the Hamiltonian that arise due to all of these interactions. Now, there are many ways to calculate something like self-energy. There are a set of Feynman diagrams that you can use to calculate this self-energy. And in the third week, we may have some time to discuss that, but you'll definitely do this in the field theory course. These are essentially diagrams that have interactions, but you don't have any external lines connected to them. So we will discuss this in more detail later on. But the idea is that you will get corrections to the single particle terms in the Hamiltonian due to interactions. And then this new Hamiltonian you can use to calculate physical quantities, physical observables, and then compare with experiments. So that's the goal. That's what mean field theory really does. Now we are going to do it more formally. So consider a system I'm not writing hats, these are all operators. So H naught, the free particle Hamiltonian or the single particle Hamiltonian. So we start in a system that has two species of particles. What do I mean by that? So the H naught has a term which involves A operators and a term that involves B operators. So these nu and mu, these are some quantum numbers. If you use momentum eigenstates to define these for second quantization, then these will be the momentum values. V interaction is nu prime, mu prime, So in this Hamiltonian, I've assumed a very special form of interaction, which is only interaction between A particles and B particles. So I'm ignoring any two particle interactions. So A particles can have two particle interactions with themselves. So two A particles, they can also interact. Two B particles, they can also interact. But I'm right now, for simplicity, assuming that there are A particles, there are P particles, B particles, and there's interaction between them. So what that really means is, if you think of it in terms of a diagram, you have A particle and B particle. Let's draw B particle also with same color. So this is A particle, this is B particle coming in, they will interact, and then B particle and A particle going out. In general, you will have two body interactions between A and B themselves. They are for the moment ignored. So we want to get the idea of mean field theory first, and then apply it to a case where you have indistinguishable particles like electrons, and then get to Hartree-Fock theory. Yes. Is there a question? So formally, to do mean field theory, we'll define what are called deviation operators. So we define that some operators d nu prime. This is defined as a nu dagger a nu prime minus its expectation value. So these are just some new operators that we have defined, and we can write the interaction term in terms of these new operators. Now, see, if we move this, so V interaction, I'm going to write it like this. I'm going to bring the A operators, so A and B operators, because I'm moving it twice. Because they are different operators, they commute. I'll just write it like this. And now this I can write as D nu prime plus the expectation value. And similarly for B, and then expand this, what I will get is, this is sum over nu prime, mu prime, V nu prime. Now, what mean field approximation formally says is that we ignored this term. So the approximation really is ignoring this term. So this is the approximation. Now, sometimes there are arguments, there are physical arguments that you can make, that you expect this term to be small, but this is not usually the case. So this is really the approximation, and with this approximation, now you can ignore this term, and in the remaining terms, put this values, the D and E operators in terms of A and B again, and you can write down what you will get is V interaction potential is sum over nu prime, mu prime, So this is really defined as V mean field. And then you can define mean field Hamiltonian, H mean field as H naught plus V mean field. So to calculate H mean field, you need to know V mean field, and to calculate the interaction potential within the mean field approximation, you need to know these expectation values. So how do we calculate these expectation values? This we will do self-consistently. So a crucial aspect of mean field theory is to calculate these expectation values in a self-consistent manner. So how do we calculate expectation value of these operators? For example, a new dagger, a new prime. This you can calculate as 1 over the partition function trace e to the power minus beta h, a new dagger, a new prime. Where z is e to power minus beta h, it's the partition function. So to calculate these expectation values, you need to know h. And to calculate h, you need to know expectation values. So do it self-consistently. What that means is guess. You can start with anything. Guess these values, a new dagger, a new prime, and b mu dagger, b mu prime. And then using this guess, you can calculate h. Once you have h, calculate these expectation values again using this h. Now these expectation values will be different from the guess most of the times, and then use these expectation values to calculate new Hamiltonian. Use new Hamiltonian to calculate expectation values, and keep doing this till the expectation value you put in to calculate h are same as the expectation values that you calculate using the new h. Keep doing this, and eventually you will have calculated the expectation values self-consistently. Yes.
So when you say H, do you mean H mean field or?
Yes. So right now, this H will be one involving H mean field, but with these expectation values. So I'm reserving H mean field for the one where expectation values have already been put in self-consistently. So let me define H mean field. So this H, once you have arrived at the final self-consistent, then you can calculate the H. This will be called HMF. So what that really means is expectation value of a new dagger, a new prime, for example, in the mean field Hamiltonian is going to be 1 over the partition function, which I also put mean field because it is e to power minus beta h mean field, and trace e to the power minus beta h mean field, a new dagger, a new prime. You will have similar expressions for the B operators, and that's it. So that defines the mean field Hamiltonian. So the idea is just do it consistently. Now, it's the mean field actually doing mean field approximation is still very tricky. The reason being the following. So we need to calculate these expectation values self-consistently. A mu dagger a new dagger, a new prime. Say the system has n quantum numbers. So how many values this can take? N. Similarly, this new prime, n. There are n square ways of choosing these operators. So there are a lot of ways you can do mean field theory. You can. So the point here is simply that there is no unique choice of these operators or quantum numbers that you should do. Typically, this is motivated by what you're after. So what I mean by that is if you want to explain a phenomena that you've seen in the lab, you have some idea about what the results say about conductance or about electronic density, whether you have charge, density wave, or so on. Corresponding, so you already have some physical insight, but you want to make concrete predictions on this state of the system. So you use physical insights to choose these operators. And this physical insight helps us a lot. We will take some specific examples later on and see how that affects the mean field theory itself. So there are many ways to choose these expectation values. So it can be very tricky when you actually go and do this for a real system. Also, whenever you do an approximation, you should always verify whether it's a good approximation or not. So see how your theory or your predictions, whether they stand the test of experiments or not. And if not, choose other quantum numbers. Maybe that will work if you're lucky. If you're really unlucky, then this method completely fails. Then there are some other methods that go beyond mean field theory. And then you can use some of those methods that is basically adding fluctuations to the mean field result. So which is essentially saying that these deviation operators, you can add small, so the average is, it's not just this some constant, but there is some small fluctuating operators around this. And you can, so there are some other methods also that you can go, but it's good to start with the simplest one first. Any questions so far?
Yes.
Yes.
Will this process of guessing, calculate, will always converge to that, or you could be like?
Yeah, it will converge. The question is how many steps it takes. So it really depends on. Sometimes you can make a very bad guess, and it can take forever. But so even the guess, it's better. Well, sometimes just guessing zero works, but don't just always guess zero. And so you may have to be a bit clever with the guess. Yes?
Earlier you mentioned we were considering the temperature zero case, and now we're doing beta, an explicit beta here in the trace.
Yeah.
Does the situation simplify if we just put in beta is infinity?
Yeah, so this I just wrote down as a general definition of how to calculate expectation value. But we will see that if we include the effect of temperature in it, in general you can include, but zero temperature case is a bit easier. In fact, you can, at zero temperature, what essentially you are doing is you are calculating this expectation value in the ground state. And for next one or two lectures, we are going to do t equal to 0. So we won't use this formula. At ground state, we will just have string of operators and we calculate expectation value in ground state. So zero temperature case answer is much easier. In fact, so I don't have time to do Hartree-Fock theory, but what I will do, have you already seen Wick's theorem in field theory? So what I will use is also it's Wick's theorem, but it's written in a slightly different form. So I'll choose next few minutes just to show it today. So the goal where we are headed on Monday when we start, we'll do Hartree-Fock approximation. the idea is we want to do mean field theory, but now these A and B type of particles, they are same. So they're indistinguishable. So you have interactions between electrons. In that case, you will need to calculate expectation value of operators like this, of 4 operators like this. What Wick's theorem says is that when you have a string of C operators, expectation value of a string of C operators, you can always break it down into product of expectation values of pairwise C operators. What that really means in this case is that this operator and these pairwise expectation value of the pairwise operators, these are called contractions. So you do all possible contractions and you can derive a general result. What that really means for this case is that this quantity is equal to C nu dagger C nu prime, C mu dagger C mu prime minus C nu dagger C mu prime C mu dagger C nu. Now there's a lot of difference in this notation and the field theory one. You dealt with fields. These are now C operators, and the crucial point is to remember what we discussed earlier. Don't just put C acting on this state to be 0. This is expectation value in ground state, which has a lot of particles. In fact, we have a few minutes, we can just show this. So for this expectation value of these 4 operators at 0 temperature, for this to be non-zero, you must annihilate a particle with momentum less than kf. Then the second particle you annihilate must also be with momentum less than kf. And then you must create 2 particles with momentum less than kf. So you fill these 2 states and then you get back to the same state and you'll have a non-zero expectation value. The main point of this Wick's theorem, where you have 2 terms, is because once you destroy 2 particles, you can create them in any order. So you can quickly show this. I'm sure you have already seen this. I will just write down the result. Use the anti-commutators to show that just this general product. So you can write C nu dagger this as delta mu mu prime minus C mu prime C mu dagger C nu. So I'm not going through the algebra, it's pretty straightforward. Just do anti-commutators to write. I'll just write down the final expression. This is equal to delta nu nu prime delta mu mu prime minus delta mu mu prime C nu prime C nu dagger minus delta nu mu prime delta mu mu prime plus delta mu nu prime C mu C nu dagger C mu prime plus delta nu mu prime C nu C mu dagger minus C mu prime C nu dagger C nu prime C mu dagger. The main idea is in field theory you do this normal ordering to help that the annihilation operator destroys everything. Here I've just put the creation operator on the, so that acts first on the right, and we have already figured out that all of these momentums are below kf. So if you want to create something below kf, you simply cannot do, because that state is already occupied and Pauli exclusion principle blocks you from doing it. So all of the things will be 0 other than these two delta functions. And now take expectation value. So you'd have expectation value. What this is simply expectation value of C nu dagger C nu prime. So you annihilate, destroy the delta function. And what this is simply C mu dagger C mu prime. Likewise, this is that. Hence, we've shown Wick's theorem for this simple case of 4 C operators. By the way, this theorem applies to a very large string. We will restrict our discussion to 4 operators as this is relevant for the Coulomb interactions. Okay, so let's end here and we'll use this result on Monday for Hardy-Fock theory. Any questions? Yes.
So for bosons, we'll have a plus, right?
So for bosons, you can do the whole calculation. I think for bosons, you might not have to worry about the signs here. So it's in general for bosons, you don't have Pauli's exclusion principle also, right? So it's a very different ball game there. So here we really use, the key idea is we use the fact that writing these operators to the right is helpful to us in the ground state because it vanishes. For bosons, we don't have Fermi C. We in fact have these condensates. So there are very interesting interacting problems for bosons also. It depends on time, how much time we have. We can discuss some of them. Any other questions? Yes.
Why does that C have to create a particle with atom less than the Fermi?
KF. So our goal is to calculate expectation value of these 4 operators. The only way this term can give you a finite result is if this so we assume that the ground state is orthonormal to all other states in the system. So first you're annihilating annihilating a particle. So this nu prime must be less than KF. Now you have n-1 particles. You want to annihilate another particle, it must be also less than KF. So now you have n-2 particles. A state with n-2 particle will have a finite overlap only with, so now you want to create 2 more particles. So again, you have n particles and then you have finite overlap. But now these 2 particles, you have to precisely calculate 2 once you destroy it. But you can do them in any order. And this fact that you can do in any order gives rise to these different terms. So we have just shown that all of these nu prime, mu prime must be less than Fermi wave vector. Any other questions? Okay, thank you.